Alright, today we're going to spend most of the time talking about derivatives of log functions, or the natural log functions, that is. So we're going to find the derivative of each one of these. So I'm just going to jump right into this. We talked about yesterday defining the derivative as being 1 over whatever follows the natural log. So it's 1 over 2x squared plus 1. And then we'll take the derivative of that part, which is 4x. We could then rewrite this as 4x over 2x squared plus 1. That's as far as I'm going to take this as far as simplifying it. The second example, before I start taking this derivative, I want to go ahead and rewrite it. By rewriting it, what it does is allow me to use the properties before I take the derivative, which makes the derivative much more easy to find. So I'm going to go ahead and rewrite it again by bringing this exponent out front using the properties. And now I'll be ready to take the derivative. So when I take this derivative, I'll leave my constant alone. I'll take the derivative of the natural log, which would be 1 over x squared minus 4 times the derivative of this part, which is 2x. I can simplify this just slightly by crossing out my 2's, multiplying those together. Or dividing those 2's, I really should say. So I end up with an x over x squared minus 4. The next one, again, I'm going to want to use the rules first because that will make the problem much easier. So I use the rules of the division, which would separate them by subtraction. So now I have the natural log of 2x minus the natural log of x plus 3. And I'll take this derivative. The derivative of the natural log of 2x is 1 over 2x times this portion, or the derivative of that portion, which would be times 2, minus 1 over x plus 3. The derivative of this portion happens to just be 1. So my answer would be 1 over x minus 1 over x plus 3. Now the only thing else I could do in this problem is make a common denominator. Chances are common denominators may be something that is given multiple choice goes. In this next problem, what you have is you have the ln of the absolute values. The reason why the absolute values are there is because natural logs are only ever positive, so we need to make sure that we include the absolute values so that we make sure our secant and tangent are always positive as well. So what we're going to do is just go straight into taking the derivative of this because we can't use any properties. So we'll write 1 over secant x plus tangent x. And then we'll take the derivative of this portion. The derivative of secant is secant x tangent x. And then the derivative of tangent is secant squared x. So let's look at how this might be simplified. So on top I'd have secant x tangent x plus secant squared x over, I'd have secant x plus tangent x on the bottom. Notice I actually have in common a secant x up top. So I'd be left within the parentheses tangent x plus secant x. So I pulled out a secant x out of both of those. What that actually did now was allow me to be able to simplify the bottom and eliminate the bottoms. So I get my final answer just to be secant x. Okay, in this problem, I'm not going to use the graphing calculator, and you don't need to do that either. What we are going to do is we're going to find the equation of the tangent line of f at the given point. So I'll just jump right in by finding the derivative because that would give me my slope. The derivative of 4 is 0, and the derivative of negative x squared is negative 2x. Then I have minus, I would put 1 over the 1/2 x plus 1. And then I'll multiply that times the derivative of the 1/2 x plus 1, which is 1/2. What that gives me is an answer of negative 2x squared minus, I really have 1/2 is being multiplied together, so we could off to the side do this little problem. 1/2, or 1 over 1/2 x plus 1 times 1/2. So when you distribute this through, you'd end up getting 1 over half of 2, which is just x, and then you'd have 1 times 2, which is 2. Then what I can do is plug in 0. Now you could have plugged in 0 up here and got the same answer without simplifying. We'll end up getting 0 minus, plug in our 0 here for our x, and I end up getting a negative 1/2 for the slope of the line. So the equation of this line would be y minus 4 equals the slope negative 1/2 times x minus 0. Again, I was using this point to find the equation of the line. This next one talks about using implicit differentiation. You need to use implicit differentiation because it's got y's in here, we can't solve for y. On this problem, we probably could make it much easier by using the rules of ln. So I'm going to break this up into the ln of x plus the ln of y, because I have a product there, plus I'd have 5x equals 30. Now I'm going to go ahead and take the derivative. So the derivative of ln x is 1 over x, plus the derivative of ln y is 1 over y. But since it's not an x, I'm taking the derivative with respect to x. I've got to remember to put a dy over dx, plus the derivative of 5x is 5, and the derivative of 30 is 0. So now I'm just going to solve for dy over dx. So I'm going to move my 1 over x to the other side, and I'm going to move my 5 to the other side. So I have a negative 1/2, or negative 1x, negative 1 over x, plus a negative 5. Then what I need to do is multiply by y on both sides. So I have y times this quantity. And I'll go ahead and leave my answer in that form. You could make a common denominator and then multiply the y through. This next example, we're going to show that the function is the solution to the differential equation. What that means is that we're going to solve, or we're going to find the derivative of this, and then what we're going to do is that derivative in this equation to prove that it's a true statement. So I'm going to go ahead and find the derivative. This is a product rule right here because of two x's being multiplied together. So I have to do first times the derivative of the second plus the second, which is the ln of x times the derivative of the first, which is 1, minus the derivative of 4x, which is 4. So I end up getting a 1 plus ln of x minus 4. So my derivative ends up being just simply ln x minus 3. Now let's take that derivative and plug it in over here to see if we get a true statement. So I have x plus y minus x, and I'm going to substitute in ln x minus 3 equals 0. Well, the other thing I need to do is I've got to show that this equals 0, so I need to make one more substitution, and that's for y. So instead of writing y, I'm going to write what y equals. It equals x ln x minus 4x. Now I have minus x ln x minus 3 equals 0. So is this a true statement? Well, I'll have to distribute my negative through and my x, so I get a negative ln x plus a 3x. Notice that everything cancels out. So as I said, everything did just cancel out. If you see I had a 1, had a negative 4, that would give me a negative 3 plus a 3. That's 0. And then an x and a negative x, which gives me 0. So this is the solution to this differential equation. The last example is we're going to locate any relative extrema and inflection points. We can confirm so max and mins occur at the first derivative. So I'll go and find the first derivative. Then what I'm going to do is set that equal to 0. If I do that, I move my 1 over x to the other side, and I solve, I get 1 equals x. So I know that at x equals 1, there's a critical number there. x equals 0 gives me the derivative being undefined, so it's also another critical number, but that is not defined for f, so not a critical number. If I plug 0 into there, it doesn't exist, is my point. So the only number I need to test is 1. I'm going to use the second derivative test in order to test this. So I'm going to go ahead and take my first derivative and rewrite it over here. The second derivative test will test the concavity and tell me whether this is a max or a min. So I'm going to bring this out front, and I get, this is first of all 0, and then I get a positive 1, and I have x to the negative second. So my second derivative is 1 over x squared. Well, if I take and plug 1 in here, I see that I have, so I'm testing this actually in the second derivative to test its concavity. I already know it's a critical number, so I know it's a max or a min. If I plug 1 in, I find out that it's positive, so it means it's concaved up. So this has to be a minimum. So I know that 1 comma something is a minimum. You can actually find that point by plugging it back into the original 1 minus ln 1. Well, 1 minus ln of 1, 1 minus 0 is 1. The only thing else I was supposed to find out is whether there was any inflection points. But no matter what number I put in for x, this is always positive. So the second derivative is always greater than 0, which means it's concave up everywhere. So there will be no points of inflection because it is concave up everywhere.